The Kirchoff's voltage law, or KVL, states that the algebraic sum of the potential rises and drops around a closed loop is zero. Now, what does the potential rise and drop mean? Potential rise and drop. First, let's draw a simple circuit. So we have the source and then resistor, and a closed loop. Okay, let this be R1, R2, and this is E. So every load or every resistor is a voltage drop. Okay, the voltage drops as it goes through a resistor. So this would be voltage drop VR1, and this would be voltage drop VR2. And voltage rise is the voltage that is applied, and the only voltage that's been applied here is the E. So this is voltage rise. Now, according to KVL, since this is in a closed loop, the sum of all of this will be zero. So E plus VR1 plus VR2 is equal to 0. Okay, that's KVL. Now we can write that as a formula, something like VR1 plus VR2. We can just write V1 actually. Yeah. So V1 plus V2 plus V3 plus ... Vn, as many as we have within a single closed loop, equal to 0. Okay. And now this KVL formula applies only for series circuits. Notice that this is a series circuit, because only series circuits are a closed loop. Parallel circuits are not a single loop. They're multiple loops. But series circuit is a single closed loop, and so KVL is applied only within series connections. Now let's do some questions to make things more clear. This is a series circuit, a single closed loop, so we can apply KVL here. Now, first thing to do is we assign the polarities. Now, for sources, we know the larger side is plus and smaller side is minus, so that's it. But for resistors, we can assign whatever we want. We can do it plus minus, plus minus, plus minus, or we can put minus, plus minus, plus minus, plus. We can assume whatever we want. I'm assuming plus and minus, plus minus, plus minus. You can assume whatever you want, but it has to stay consistent for every resistor. It has to be the same order: plus minus, or minus, plus minus, plus. And again, E2, it's the same. Larger one is plus and smaller one is minus. So applying KVL, we have E1. Now, will it be plus or minus? See, E1, and then the current emitted from here, it enters through plus. Whenever current is entering through plus, it will be a minus in the formula. So E1 minus VR1. Again, going through R2, entering through plus. So minus VR2. Again, for E2, it's entering through plus. So again, minus E2, equal to 0. So this is KVL being applied here. Now, we have to find VR1, right? Let's do it in the next page. So E1 was 16 volts. 16 minus VR1 we have to find. And VR2 was 4.2 volts. And E2 was minus 9 volts. So equal to 0, right? See, here's the formula. We just substitute the values. And now we find VR1. So minus VR1 is equal to minus 16 plus 4.2 plus 9. So VR1 is equal to minus 16 plus 4.2 plus 9. That is minus 2.8 volts. Minus 2.8 volts. So that's our answer for VR1. Now let's do another question. So KVL, it's another series circuit, closed loop, but we have to find Vx, which is in the middle, in between the circuit. So this Vx essentially divides the circuit into two parts. This loop is part 1 and this clockwise loop is part 2, right? So we can actually find Vx using either of these loops. We'll use both just for explanation's sake. First, let's do with the first loop, left side. So we have E1. Again, assigning the values larger side is plus and smaller side is minus, but for resistors it's just assumption. So plus minus, I'm using plus minus and plus minus. You can use whatever you want, but be consistent for each resistor. It has to be the same. Now E1 minus R1 VR1 minus VR1, because as you can see it's entering through plus. Entering through plus means minus in the formula. So E1 minus VR1, and then again minus Vx entering through plus. See, Vx has polarity as well, plus and minus, and it's entering through plus, so minus Vx equal to 0. That's KVL being applied. Now let's take it to the next page. E1 is 32 and R1 is 12, VR1 is 12. So we have 32 minus 12 volts and again minus Vx equal to 0. We have to find Vx. So minus Vx is equal to minus 32 and plus 12. Therefore Vx is equal to 32 plus 12 minus 32 plus 12 minus 20, but minus cancels out, so we have 20 volts. Okay, that's the answer. Now for the next loop we'll get the same answer. So let's see, we'll start from here from Vx. Starting from Vx, it's minus to plus, so we'll put Vx plus Vx, and then entering through plus, so minus VR2, and again entering through plus, so minus VR3 equal to 0. That's KVL. You can just do it here. So Vx, substituting the values, so Vx minus 6 volts, again minus 14 volts equal to 0. So Vx is equal to minus 16 minus 14 is 20, and minus 20 goes that side, so it's plus 20 volts, which is the same as we had here. Same value, because it's the same thing, we just changed the loops. Now let's do another question. This doesn't look this doesn't look like much of a circuit anyways. Doesn't look like much of a circuit. Okay, so but we don't care about that. It's plus and minus. We'll just find V1 and we'll find V2. This is plus here and minus. So 25 volts is, let's start KVL for the first loop, 25, and then entering through plus for V1, so minus V1, and then entering through minus for 15, so it'll be plus 15 equal to 0. So V1 is equal to minus 25, minus V1 is equal to minus 25 and minus 15. So V1 is equal to minus cancel, so 40 volts. That's V1. Now for the second loop we start from V2. Now notice that for V2 the current is coming out of minus. Coming out of minus means it's entering through plus, right? So again, using that entering through plus thing, it means we have to put a minus first. So V2 minus V2, and then again entering through plus, so minus 20 equal to 0. So what's V2? V2 is equal to minus 20 volts. Now we're done with this. Let's go to Kirchoff's current law, KCL. Now KCL states that the sum of the currents entering a junction of a network, let's first explain what a junction is. So junction is a point in a circuit which divides the circuit into multiple branches. So if this is a part of a circuit, and we put a junction here, bring out another branch, this is a junction, it's a node, junction or node, whatever you want to call it. It can have as many branches as you want. So this is a junction. So the sum of the currents entering a junction of a network must equal the sum of the currents leaving that junction. So current entering must equal to current leaving for every junction. So let's draw another junction here, and let's say 6 amperes are entering. So, and let's say two branches are exiting, right? So two branches exiting means the sum of both branches must equal 6. So it can be 3 amperes and 3 amperes, or it can be 4 amperes and 2 amperes, because that also equals 6, or it can be 5 amperes and 1 ampere, because that also equals 6. So whatever it is, it just has to be equal to whatever current entered the junction. So current entering is equal to current leaving. Now KCL is only applicable for parallel connections, because only parallel connections like this one, as you can see, parallel connections have junctions here on nodes, multiple branches. But series connections don't have any nodes, it's just one single loop. So we cannot apply KCL to series circuits or series connections. We can apply KCL only to parallel connections. Let's go through some questions to make things more clear. So we have half of a circuit, but again that doesn't matter. We want to find I1 and I2, and we have everything needed to find that. So this is a junction because multiple branches are branching out, and we can see 5 ampere enters, 5 amperes enter the junction or the node, and I1 and I2 are branching out, exiting. I2 is 4 amperes. We have to find I1. Applying KCL, current entering, so 5 is equal to current leaving. So I1 plus I2. And now in the same sides, we always add them up. So if multiple currents are leaving, we add them up in the right side. And if multiple currents were entering, we would add them up in the left side. We'll get to that later. So 5 equal to I1 plus I2. Let's substitute the values. So 5 is equal to, what's I1? I1, we have to find I1, but I2 is 4 amperes. So I1 plus 4. Now just shifting things around, we can get I1 is equal to 5 minus 4, so 1 ampere. That's our answer for I1. I1 is 1 ampere. We can verify that. See, 4 ampere exited for I2, so it has to be equal to 5 ampere entering. So I1 will obviously be 4 plus 1, 5 amperes. So 1 ampere. I1 will be 1 ampere. Now, what is I3? Now note that I1 and I2 exit from this junction, but then again they come back and join this junction, right? Now if we skip all of this, 5 ampere entering here will also be 5 ampere exiting here. So I3 will be equal to 5 amperes. So we don't even have to calculate for that. It's the same, because whatever current is entering from here is coming back to this junction. Nothing is going to another branch or something. Now let's do another question. Again, half of a circuit, but doesn't matter. We have what we need for finding I3. We have to find what is I3 and what is I5. This here's I3 and I5. Now for I3, notice that here we have a junction, so I1 is entering. Again, notice here that I2 is also entering the junction and I3 is exiting. So what that means is I1 plus I2, because two currents entering, is equal to the only current leaving, so I3. Let's substitute the values. So we have I1 is 4 amperes plus I2 is 3 amperes is equal to I3. Therefore I3 is equal to 7 amperes. So I3 here will be equal to 7 amperes. Now we have to find this I5. Again, notice that I3 enters a node here, or a junction, and so I3 is entering, I4 and I5 are leaving, right? So again, applying KCL, we can write I3, the only current entering, is equal to I4 plus I5, the currents that are leaving. Now we have the value of I3, which is 7 amperes. We just calculated that. And we also have I4 given as 1 ampere. So is equal to 1 ampere plus, let's just erase this ampere. Okay. So 1 ampere plus I5. We have to find the value of I5. Let's shift things around. I5 is equal to 7 minus 1, so 6 amperes. That's I5. You can again verify that. 6, so 6 here and 1 here. 6 plus 1 will equal to 7 here. So the answer is correct, 6 amperes. That's KVL and KCL. They're really easy to understand and they're very helpful for analyzing circuits.